Imagine standing in the heart of ancient Rome on a sweltering summer morning in 118 AD, watching thousands of workers swarm like ants across what would become the most impossible architectural achievement in human history. The air is thick with limestone dust and the acrid smell of burning lime, while the rhythmic pounding of bronze hammers against stone creates a thunderous symphony that echoes off the seven hills. Emperor Hadrian has just announced his most audacious project yet, a temple so vast, so technically challenging, that even Rome's master builders whisper it cannot be done. Tonight, we'll follow the extraordinary journey of how human ingenuity, Roman engineering genius, and sheer determination transformed this seemingly impossible dream into the Pantheon, a structure that still defies understanding nearly 2,000 years later. Gaius Apollodorus stepped carefully through the construction site, his trained eye scanning every detail of the organized chaos surrounding him. As Hadrian's chief architect, he bore the crushing responsibility of turning the emperor's grand vision into reality. The morning sun cast long shadows across the Campus Martius, where hundreds of workers were already at their tasks, some hauling massive blocks of travertine on wooden rollers, others mixing the revolutionary concrete that would make this project possible, and still others carefully measuring and marking the precise locations where walls would rise. At 52, Apollodorus had already earned legendary status among Roman builders. Born in Damascus to a family of Syrian craftsmen, he had learned the ancient secrets of stone cutting and bronze working before being brought to Rome as a young man to work on Trajan's Forum. His innovative use of concrete and steel understanding of structural engineering had already transformed the Roman skyline. But the Pantheon would be different. This wasn't just another temple or public building. It was Hadrian's statement to the world that Roman engineering could achieve the impossible. The emperor himself had been unusually specific in his requirements. The new Pantheon would completely replace Agrippa's earlier temple, which had been damaged by fire decades earlier. But Hadrian's vision went far beyond simple reconstruction. He wanted a dome larger than any ever attempted, a perfect hemisphere that would seem to float weightlessly above the temple floor. The mathematics alone were staggering. A concrete dome spanning 142 feet would weigh over 5,000 tons, creating structural loads that pushed the limits of what stone and mortar could bear. Walking through the crowded streets of Rome that morning, Apollodorus made his way to the workshops where his teams were developing the techniques that would make the Pantheon possible. The secret weapon in their arsenal was Roman concrete, a revolutionary building material that most of the ancient world had never seen. Unlike traditional construction that relied on carefully fitted stone blocks, concrete could be poured into any shape and would harden into artificial stone stronger than many natural materials. The discovery of concrete's potential had been one of those happy accidents that occasionally change the course of history. Roman engineers working on harbor projects around the Bay of Naples had noticed that local volcanic ash, when mixed with lime and water, created a mortar that not only set underwater but actually grew stronger with time. This volcanic ash, which the Romans called pulvis putiolanus, contained silica and alumina that reacted chemically with lime to form compounds similar to those found in natural stone. But creating concrete was only the beginning of the challenge. The Pantheon's dome would require concrete of different weights and strengths at different elevations, demanding a level of technical sophistication that pushed Roman engineering to its absolute limits. At the base of the dome, where structural loads were greatest, Apollodorus planned to use heavy concrete loaded with chunks of travertine and basalt. Higher up, the mixture would gradually transition to lighter aggregates, first tufa stone, then broken pottery, and finally, at the dome's crown, pumice so light it would float on water. The construction process began with foundations that would have impressed modern engineers. Teams of slaves and freedmen excavated through 20 feet of accumulated debris, broken pottery, discarded building stones, and the accumulated refuse of centuries of urban life, until they reached the solid clay that lay beneath Rome's marshy ground. Here, in a massive circular trench, Apollodorus's crews began laying the foundation ring that would anchor the entire structure. The foundation wasn't simply a platform of stones, but a carefully engineered system designed to distribute the Pantheon's enormous weight across the soft Roman soil. Each block of travertine was precisely cut and positioned, with joints so tight that no mortar was needed. The stones were arranged in a complex pattern that created multiple load paths, ensuring that if one section of the foundation settled slightly, the loads would automatically redistribute to stronger areas. Roman understanding of soil mechanics, while lacking modern scientific terminology, was remarkably sophisticated in practical application. Apollodorus knew that the marshy ground near the Campus Martius would compress under the Pantheon's weight, so the foundation was designed to settle evenly rather than resist all movement. The massive weight of the foundation stones themselves would pre-compress the soil, reducing future settlement once the building was complete. As autumn arrived in 118 AD, the real construction began with the rising of the Pantheon's walls. Roman builders employed a technique called opus mixtum that perfectly demonstrated their engineering genius. Rather than constructing solid stone walls, they built frameworks of brick and filled the spaces between with concrete. This approach was lighter than solid masonry, faster to build than traditional stone construction, and infinitely more flexible in creating complex architectural forms. The concrete itself represented the cutting edge of ancient material science. Roman cement makers had spent decades perfecting their recipes, testing different combinations of volcanic ash, lime, and water to achieve specific properties. The ash came from carefully selected deposits around Naples, where different volcanic eruptions had created materials with distinct characteristics. Ash from Pozzuoli created concrete that could set underwater, while deposits from the Alban Hills produced especially hard mixtures ideal for load-bearing applications. The mixing process was as critical as the ingredients themselves. Roman builders understood that concrete had a limited working time after mixing, and that the proportions of ingredients had to be precisely controlled to achieve consistent results. They developed standardized measuring vessels and mixing techniques that ensured quality remained consistent from batch to batch. The work was typically supervised by experienced foremen who could judge the quality of a concrete mix by its color, consistency, and even the sound it made when mixed. But perhaps the most ingenious aspect of Roman concrete construction was their systematic use of different aggregates to control weight and strength. Aggregate selection wasn't random. It was based on careful understanding of how different materials behaved under structural loads. Heavy aggregates like travertine chips provided maximum compressive strength for foundations and lower walls. Lighter materials like tufa and broken pottery reduced weight while maintaining adequate strength for less critical applications. The wooden scaffolding required for the Pantheon's construction was itself a marvel of ancient engineering. Master carpenters designed temporary structures that could support not just workers and tools, but the enormous weight of wet concrete as it cured. The scaffolding systems incorporated elements borrowed from siege engine construction, shipbuilding, and military engineering, creating hybrid structures that could bear incredible loads while remaining stable in wind and weather. Roman carpenters had developed sophisticated joinery techniques that allowed them to create incredibly strong wooden structures using only bronze tools and wooden fasteners. Iron nails were expensive and prone to rust, so most connections relied on carefully shaped wooden joints, mortise and tenon, dovetails, and complex interlocking systems that actually grew stronger under load. The scaffolding for the Pantheon used thousands of precisely cut timber pieces, all joined with techniques that had been refined over centuries of construction experience. The carpentry work also had to account for the natural behavior of wood as it dried and seasoned. Green timber would shrink and move as it lost moisture, so Roman builders designed joints and connections that could accommodate this movement without losing structural integrity. The scaffolding systems incorporated adjustable elements, wedges, jacks, and sliding connections that could be modified as the wooden framework settled and adjusted. As the Pantheon's walls rose higher, Apollodorus faced one of the most challenging aspects of concrete construction, creating openings for doors and windows without compromising structural integrity. The solution came from the Roman mastery of arch construction. By embedding wooden forms in the concrete and removing them once the mixture had cured, builders could create perfectly shaped openings that actually strengthened the wall by redirecting structural loads around the void. This technique, known as void forming, required extraordinary precision in both the construction and removal of wooden forms. The forms had to be strong enough to resist the pressure of wet concrete being poured around them, yet designed for easy removal once the concrete had hardened. Roman carpenters developed specialized tools and techniques for extracting these forms without damaging the surrounding concrete, often using tapered designs that could be driven out with bronze wedges. The architectural details of the Pantheon's interior required even more sophisticated forming techniques. The great coffers that decorate the dome's interior surface weren't merely decorative, they served crucial structural and practical functions. Each coffer reduced the dome's weight while creating a pattern of reinforcing ribs that helped distribute structural loads. The coffers also provided convenient anchor points for the bronze rosettes and decorative elements that would complete the interior design. Creating these complex three-dimensional shapes required wooden forms that were essentially reverse sculptures, precisely carved to create the desired interior spaces. The forms had to be mathematically accurate. Any deviation from the intended curves would create weak points where the concrete might crack under load. Roman carpenters used bronze templates and geometric construction techniques to ensure that every coffer was identical in size and shape. The year 120 AD brought the greatest challenge of all, construction of the dome itself. No concrete dome of this size had ever been attempted, and even Apollodorus wasn't entirely certain his calculations were correct. The dome would span 142 feet, weigh over 5,000 tons when complete, and somehow had to support itself without any internal columns or external buttresses. The secret lay in the Roman understanding of how arch principles could be extended into 3 dimensions. Construction of the dome began with the most ambitious wooden framework ever attempted in the ancient world. This centering, as it was called, was essentially a complete wooden dome built from the ground up to support the concrete until it could cure and become self-supporting. The framework required over 200 tons of carefully selected timber, all cut to precise curves and joined with bronze fittings that could be disassembled once the concrete had hardened. The curves of the wooden centering had to be mathematically perfect. Any deviation would create stress concentrations that could cause the finished dome to crack. Roman carpenters used a technique called striking centers to create these perfect curves, starting with a central point and using bronze compasses with extended arms to scribe perfect arcs on the wooden framework. Each piece of timber was then cut to follow these curves exactly, creating a structure that was geometrically precise despite being built entirely with hand tools. The wooden centering also incorporated one of the most ingenious aspects of Roman engineering, the system for its own removal. The entire framework was designed to be lowered gradually once the concrete had cured, allowing the dome to settle onto its own structure without sudden shock loads that might cause cracking. This required a complex system of wooden wedges, bronze jacks, and adjustable supports that could be operated simultaneously by teams of workers following carefully rehearsed procedures. The concrete for the dome was mixed and placed in a series of horizontal lifts, with each layer allowed to partially cure before the next was added. This technique prevented cracking from uneven shrinkage and allowed the builders to adjust the concrete mixture as they worked higher up the dome. The process required extraordinary coordination. Each lift had to be completed in a single day to ensure proper bonding between layers, which meant that hundreds of workers had to maintain a steady pace of mixing, carrying, and placing concrete for up to 12 hours at a time. At the base of the dome, Apollodorus used the heaviest concrete mixture in his arsenal, loaded with chunks of travertine and basalt that provided maximum compressive strength. As the dome curved inward, the mixture gradually transitioned to lighter aggregates. The middle sections used tufa stone and broken pottery, while the uppermost portions incorporated pumice that was so light it would actually float on water. This graduated approach reduced the dome's total weight while maintaining structural integrity throughout. The pumice used in the dome's upper sections came from carefully selected volcanic deposits near Naples, where centuries of eruptions had created vast beds of naturally lightweight stone. Roman quarry workers had learned to identify the best pumice by its color, texture, and weight, selecting only pieces that met strict standards for strength and lightness. The pumice was transported to Rome in specially designed ships that could handle the unusual cargo without shifting or damage. Roman builders also understood the critical importance of curing conditions for concrete strength. They developed techniques for keeping the concrete moist during the crucial early days after placement, using wet cloths, standing water, and even steam from heated pots to maintain proper humidity levels. The chemistry of Roman concrete was such that it continued to gain strength for months or even years after placement, but only if proper curing conditions were maintained during the first few weeks. The dome's most famous feature, the great oculus that opens to the sky, served multiple functions beyond its obvious aesthetic and spiritual significance. The 27-foot opening at the dome's peak reduced weight at the point of maximum structural stress, while providing perfect balance to the forces pressing outward from the dome's base. The oculus also solved a critical construction problem: how to finish the top of a concrete dome where compression forces were most concentrated. The structural engineering of the oculus was remarkably sophisticated. Rather than simply leaving a hole in the concrete, Roman builders created a carefully designed ring beam that distributed loads around the opening. The edge of the oculus was reinforced with bronze elements that helped prevent cracking and provided a finished appearance that would endure for centuries. The precise geometry of the opening was calculated to maintain the dome's structural integrity while maximizing the dramatic effect of sunlight streaming into the interior. The drainage system for rainwater entering through the oculus represented another masterpiece of Roman hydraulic engineering. Nearly invisible bronze drains were built into the marble floor, connected to a complex network of pipes and channels that carried water away without any visible impact on the building's interior. The floor itself was constructed with a slight dome shape, sloping almost imperceptibly toward the drainage points to ensure that even small amounts of water would flow away efficiently. The interior construction of the Pantheon required techniques that were just as sophisticated as the structural work. The great columns supporting the entrance portico were single pieces of Egyptian granite, each weighing over 60 tons and representing some of the most ambitious stone transportation projects in ancient history. These monoliths had to be quarried in southern Egypt, transported down the Nile River, shipped across the Mediterranean, and somehow moved through the streets of Rome to their final positions. The logistics of moving Egyptian granite columns to Rome involved some of the most complex transportation operations of the ancient world. Special ships called obelisk carriers were built specifically for transporting massive stone blocks, with reinforced hulls and specialized loading equipment designed to handle cargoes that weighed as much as modern railroad cars. The journey from Egyptian quarries to Rome could take many months, with stops required for weather, repairs, and the complex process of transferring cargo between different types of vessels. Once in Rome, the columns had to be moved from the Tiber River docks to the construction site using techniques that pushed the limits of ancient mechanical engineering. Roman builders used systems of bronze rollers, wooden tracks, and teams of oxen to move loads that would challenge modern equipment. The process required careful route planning to avoid steep grades and narrow streets, sometimes necessitating the temporary removal of buildings or the construction of special roadways to accommodate the massive stones. The precision required for positioning these enormous columns was achieved using surveying and measurement techniques that were remarkably accurate despite relying entirely on bronze instruments and geometric calculations. Each column had to be positioned exactly according to the architectural plan, with tolerances measured in inches rather than feet. The columns also had to be perfectly vertical and aligned with each other to create the precise visual effects intended by the design. The marble veneer that covers the Pantheon's interior walls demonstrates another aspect of Roman construction genius: the ability to make expensive materials go much further through skillful application. Rather than building with solid marble blocks, Roman craftsmen cut thin sheets of colored marble and attached them to the concrete walls with bronze clamps and mortars. This technique, called opus sectile, allowed them to create intricate geometric patterns using rare marbles from quarries across the empire. The marble cutting process required skills that took decades to master, and tools that represented the height of ancient metalworking technology. Roman stoneworkers used bronze saws with abrasive sand to cut marble sheets to exact dimensions, a process that was both time-consuming and extraordinarily expensive. The sheets had to be perfectly flat and smooth, with edges cut to precise angles that would create seamless joints when installed. Any errors in cutting or measurement would result in visible gaps or misaligned patterns that would mar the building's appearance. The installation of marble veneer required equally sophisticated techniques. Each sheet had to be carefully positioned and secured with bronze clamps that were hidden within the joints between stones. The clamps themselves were precision-made components, cast to exact dimensions and designed to hold the marble securely while allowing for the slight thermal expansion and contraction that occurs with temperature changes. The skill required to install these systems without visible fasteners or support structures represented the pinnacle of Roman stone working technology. The mathematical precision behind the Pantheon's design would impress modern engineers and architects. The dome's interior diameter equals the building's height from floor to oculus, creating perfect proportional harmony that was no accident but the result of careful geometric planning. The thickness of the dome decreases from 21 feet at the base to just 4 feet near the oculus, with the reduction calculated to maintain structural integrity while minimizing weight at the most critical stress points. Roman mathematical understanding, while different from modern calculus-based engineering, was remarkably sophisticated in its practical applications. Roman architects used geometric principles and proportional systems that had been developed and refined through generations of building experience. They understood concepts like load distribution, structural redundancy, and the relationship between span and thickness that are fundamental to modern engineering, even though they expressed these concepts in geometric and empirical rather than mathematical terms. The proportional systems used in Roman architecture were based on modules and ratios that created naturally pleasing relationships between different parts of a building. The Pantheon's design incorporates multiple geometric relationships: the golden ratio, perfect circles and squares, and proportional systems that create a sense of harmony and balance that visitors still experience today. These weren't arbitrary aesthetic choices, but carefully calculated design decisions based on centuries of architectural experimentation and mathematical refinement. As the Pantheon neared completion in 125 AD, the most nerve-wracking moment in the entire construction process finally arrived: the removal of the enormous wooden framework that had supported the dome during construction. This process, called striking the centering, would determine whether Apollodorus's calculations were correct and whether the dome could actually support itself. If the concrete hadn't cured properly, or if the structural loads had been miscalculated, the dome would collapse the moment its wooden support was removed. The striking process began at dawn on a carefully chosen day when weather conditions were perfect: no wind, moderate temperature, and stable atmospheric pressure that wouldn't stress the concrete as it took its own weight for the first time. Teams of workers positioned at dozens of support points began simultaneously removing wooden wedges and lowering adjustable supports, allowing the framework to settle and separate gradually from the concrete above. The process took most of the day, with supports removed in a carefully planned sequence that prevented any sudden load changes that might crack the concrete. Hour by hour, more of the wooden framework was lowered away from the dome until finally the massive concrete structure stood completely free, supported only by its own carefully calculated internal forces. Contemporary accounts describe crowds gathering in the streets of Rome as word spread that the impossible had been achieved. A dome larger than any in history was standing on its own, defying gravity through human ingenuity alone. The successful completion of the Pantheon represented not just the achievement of a single building project, but the culmination of centuries of Roman engineering development. Every technique used in the construction had been tested and refined in smaller projects across the empire. The concrete recipes had been perfected through decades of experimentation. The structural principles had been proven in countless bridges, aqueducts, and public buildings. The Pantheon was possible because it stood on the shoulders of generations of Roman builders who had gradually pushed the boundaries of what could be achieved with stone, bronze, and human determination. The techniques developed for the Pantheon weren't limited to this single masterpiece, but spread throughout the Roman Empire and influenced construction for centuries to come. Roman concrete technology was used to build the great aqueducts that supplied fresh water to cities across the empire, the massive amphitheaters where gladiators fought before crowds of 50,000, and the basilicas that would later inspire the great cathedrals of medieval Europe. The principles of Roman engineering spread to Britain, where they built Hadrian's Wall, to Germany, where they constructed elaborate heated bath complexes, and to North Africa, where they created vast granary systems that fed the empire. The spread of Roman construction knowledge throughout the empire was facilitated by a sophisticated system of technical education and knowledge transfer that was unprecedented in the ancient world. Experienced architects and engineers traveled constantly, supervising major projects and training local craftsmen in the latest techniques. The Roman military also played a crucial role in spreading construction knowledge, as legionary engineers built roads, bridges, and fortifications that incorporated the most advanced techniques available. Roman technical literature, including treatises like Vitruvius's De Architectura, codified construction knowledge and made it available to builders throughout the empire. These texts included not just theoretical principles, but practical instructions for everything from site preparation to material selection to quality control procedures. The standardization of techniques and materials across the vast Roman Empire ensured that a building constructed in Britain would use fundamentally the same methods as one built in Syria or North Africa. The Roman building industry represented one of the ancient world's most sophisticated examples of organized technological activity. The industry employed hundreds of thousands of workers in specialized roles: quarry workers, lime burners, brickmakers, carpenters, stonemasons, bronze workers, and dozens of other trades. Each trade had its own guild system, apprenticeship programs, and quality standards that ensured consistent results across the empire and over many generations. The economic impact of Roman construction was enormous, driving demand for materials and labor that supported entire regions of the empire. Egyptian granite quarries employed thousands of workers and required massive infrastructure investments. Volcanic ash mining near Naples created a major industry that supplied cement materials throughout the Mediterranean. The transportation networks required to move building materials stimulated the development of better roads, larger ships, and more efficient loading and unloading techniques that benefited commerce throughout the empire. Perhaps most remarkably, the Romans achieved all this without the mathematical tools and mechanical aids that we consider essential for modern construction. They had no mechanical calculators, no steel measuring tapes, no power tools or heavy machinery, no computer-aided design systems or stress analysis software. Instead, they relied on geometric principles learned from Greek mathematics, empirical knowledge gained from centuries of hands-on building experience, and quality control systems that caught errors before they could compromise structural integrity. Roman measuring and calculation techniques were based on geometric principles and practical experience, rather than abstract mathematical theory. Builders used bronze instruments, water levels, and proportional systems to achieve precision that matched or exceeded what we expect from modern construction. The absence of mechanical aids was more than compensated by extraordinary skill and attention to detail that was developed through years of apprenticeship and hands-on experience under master craftsmen. The quality control systems developed by Roman builders ensured that construction errors were identified and corrected before they could compromise a project's success. Master craftsmen regularly inspected work in progress, using standardized tests and measurements to verify that materials and workmanship met established standards. These systems prevented the accumulation of small errors that could lead to major structural problems in completed buildings, ensuring that Roman structures would remain sound for centuries. As we drift towards sleep on this quiet evening, imagine Gaius Apollodorus standing in the completed Pantheon on a golden afternoon in 126 AD. Sunlight streams through the great oculus, creating a moving circle of light that travels across the marble floors as the earth turns. The impossible dome soars overhead, its perfect curves seemingly weightless despite the thousands of tons of concrete and stone that form its structure. In achieving this miracle of engineering, Apollodorus and his fellow builders had proven that human ingenuity, careful planning, and masterful technique could create monuments worthy of the gods themselves. The whispered conversations of visitors echo softly in the great space, mixing with the distant sounds of Roman street life filtering through the massive bronze doors. Merchants haggle in the markets beyond, children play in the narrow streets, and the business of the greatest empire in history continues its eternal rhythm. But here, in this perfect space created by human hands and minds, time seems suspended, as if the very air holds the memory of every chisel stroke, every carefully mixed batch of concrete, every precisely placed stone that made this wonder possible. Somewhere in the city, new projects are already beginning. Public baths that will incorporate the latest heating technology, basilicas that will push the limits of span and height, aqueducts that will carry fresh mountain water across impossible distances. The techniques perfected in the Pantheon will spread throughout the empire and beyond, inspiring builders for generations yet unborn. The Roman Empire itself may eventually fade into memory, but the principles discovered by builders like Apollodorus will endure, testament to human creativity and the eternal desire to build something lasting from stone, bronze, and dreams. In the gathering dusk of that ancient day, as oil lamps begin to flicker in the windows of Rome and the first stars appear in the darkening sky, the Pantheon stands eternal, a perfect fusion of engineering and artistry that will outlast empires and inspire wonder for thousands of years to come. The techniques that created this masterpiece represent one of humanity's greatest technological achievements, proving that even without modern tools, human ingenuity guided by knowledge, determination, and skill can create wonders that truly touch the divine.